I think it's obvious that if you go very far back in Earth's history, you cannot identify organisms themselves or fossils of the organisms, but you can identify the metabolic interaction of organisms with their surroundings. For the second part of the talk, there's going to be probably more speculation than solid data would usually allow, and I think that one could safely say that it's probably clearly not all correct. But the interesting part is that I'm almost convinced that it's not all incorrect either, so there might actually be something in there that we can use. Anyway, since we're talking astrobiology, of course we start in space and we go in closer to Earth, and what we see is a interesting place. As Uffe just mentioned, it's a low entropy system where there is has been a compartmentalization of the material into various compartments like the atmosphere, the ocean, and the continents. And for geologists, the basic question, of course, is how did such a planet evolve? How did we actually produce the continents? And how did they preserve a liquid ocean on Earth through the entire geologic history, which goes back to about 3.8 billion years. So we descend on Earth to our favorite part of Earth, of course, Greenland. And up here, just in the polar darkness, you can see the field area that we're going to visit. So we tend to change the transport mechanism from the space shuttle to more Earth-like means and go towards Isua in West Greenland. I'm sorry the colors don't come up quite nicely, but anyway, this is a geologic map, and the geologic map shows the distribution of either rock types or rock ages or something on a geographical map base. And this particular map shows you an area in West Greenland. We have ancient felsic gneisses, that is materials that are formed by the crystallization, the solidification of granite magma deep in the Earth's crust, which is all this tan-colored stuff. And then we have this multicolored arcuate device here, which is about 35 kilometers by 4 kilometers. You can see it has many different colors, and that's important because each of these different colors represent a different rock type, and all the rocks in this belt are basically formed on the surface of Earth, so they might carry some sort of memory of the surface conditions on our planet. And they are enclosed by these felsic gneisses that formed 3.6 billion years ago, so they must be somewhat older than that, and we'll get back to exactly how much older we think they are. If we look at the area as not as Anja suggested, a horrible place, it's a beautiful place. You can see there's actually some rocks sticking out, which is good if you're a geologist. What is even better is that these rocks have just recently been left by the receding ice cap, which means that they are exposed for observation, they're polished, they're nice, they're clean, washed, nothing has happened to them. So, and there's no plants or any other disgusting things to block the view. So this is really a marvelous place, and we can try to look at what kind of rocks we see in that area. This is a particularly interesting rock, and to most of you it might not seem very exciting, but it really is a spectacular rock. And the reason why it's spectacular is due to these low-bayed structures. They are pillow-shaped, and it's a rock type called a pillow lava, pillow basalt. And as you probably all know, basalt is the sort of the basic rock type you form on any rocky planet that you know of. That's just a partial melting of terrestrial planet type material. Basalt. So the fact that we have basalts way back in time is not particularly surprising or exciting, but the shape of these objects is particularly pleasing to see, because these types of structures formed when basaltic volcanoes erupt underwater. So this is the first evidence we have for the presence of water on the surface of Earth 3.7 to 3.8 billion years ago, and that is of course a very exciting finding.
So how can you date things?
Oh, I'll get back to that.
All right.
This is a very elongated pillow.
Yeah, it is
deformed.
They are deformed. They are deformed. All the rocks in this area have been subjected to hybrid metamorphism in several phases of deformation, and only very, very few little out in the surface you actually see structures preserved. Mostly everything that's made out to nothing weird.
And this is basalt.
This is basalt. This is pillow basalt. This would be what you would see if you jump around nice and big.
But I thought you have a basalt in the Isua.
Oh yes, you have plenty of metabasalt. Yes, metamorphism basalt. That's actually the main constituent of these vertical crystals. This basalt. So you have partial melting of the mantle, you have outpouring of the melt products, and you have the extrusion of this material under water. So that is very exciting, I think. We also have other rock types that suggest that this is water under at that time. This is a bent iron formation, formation. It is a rock that consists of alternating layers of magnetite, which is a iron oxide mineral, and quartz. And everybody believes that these things are formed by precipitation, or chemical precipitation, out of a aqueous solution in some sort of oceanation. So this also suggests that we have water, and this not only suggests that we have water on the surface, but also that the water was in a liquid state at that time. So this indicates to us that at 3.8 billion years ago, we actually did have atmosphere on Earth, and we probably were within the three-phase field of water already that had been in the two-phase field of water. That is, of course, as you probably all know, very exciting because of solar and change and so forth, but we're not going to that any further. We just say we know that liquid water existed in oceans already 3.7 to 3.8 years ago. And how do we know that they are 3.7 to 3.8 years ago? Well, actually, we don't. What we know is that these rocks, they formed on the surface of Earth, they were subject to deformation, metamorphism, and so forth, and after they've been deformed, metamorphosed, and so forth, they were fractured, and granite magma was pouring through these fractures and filling fractures and forming these granite dikes in the area. We cannot date the supercrustals themselves very accurately. We can date them with a precision of maybe 100 million years or something like that, and that gives us 3.75 plus minus 100 million years, which is not very accurate. But the beauty of this is that we know that they are older than these granites, and granites are very easy to date because they contain the mineral zircon, which you have here. It's called silicate. Beautiful, nice diamond-like crystals. Zircons are like diamonds, they forever in the first form zircons and hard to get left ever again. So therefore, and they're very robust, they contain uranium, which is left, and used from uranium dating. Since we have been talking about objects from clusters of galaxies down to atoms, I guess during the last session, I'm going to show you the size of zircons that we work on. These are about 30 or 40 zircons sitting on the tip of a pin of a needle. So this is the typical size of zircon crystals. So they are about a tenth of a millimeter. Very few people in here will be able to see a zircon with a naked eye. What you do to the zircons to find out the age of these rocks is that you cut them and polish them, so you just slice them through the middle, one of these little grains, and you can take it into a secondary Sims mass spectrometer, and you can make a little dent in it and analyze the uranium and lead isotopic ratios, and you can calculate the age of the zircon very precisely. And you can actually take a zircon that is almost 4 billion years ago, and you can sometimes get sub-million year precision on your age determination. So this gives you very precise ages. And what you can tell from this is that every rock in this ancient geologic complex is more than 3.7 billion years old. Many of them are more than 3.8 billion years old, but we cannot say that for all of them because some units are not cut by these particular dikes. But my personal feeling is, of course, that everything there is more than 3.8 billion years ago, more than 3.8 billion years ago. It could be up to 3.9 or even more than that, we don't know that, but definitely more than 3.7, probably more than 3.8. Within this area, there's also one unique outcrop of plastic sedimentary rocks, that is sediments deposited by the movement of grains in some sort of aqueous environment. And what you see in this particular outcrop, you see a hammer here that's about 70 centimeters long. You can see that we have these graded layers that are separated by some dark layers. The graded layers are formed in submarine avalanches, like in this model. Of course, they were originally deposited or in a horizontal manner, but you had avalanches coming down submarine slopes and falling onto the ocean floor, as it happens today, and forming these graded beds, and they formed within a few minutes or hours at that time. In quiet periods between these various avalanche periods, there was deposition of clay on the ocean floor, and the deposition rate of clay is very, very low in the oceans today, and probably also was at that time. So the clay layers are going to give us some sort of an indication of everyday, I was just about to say everyday life on Earth, but definitely about everyday conditions on Earth at that time. So the clay layers will integrate very long time periods in the most prominent and biggest and sort of most average environment on Earth in the ocean. So just for that particular reason, the clay layers are very interesting to look at. and we've been trying to go in and see what you can find in these layers. First of all, you can see that in this particular one outcrop, the clay layers are actually recognizable. Of course, they're now metamorphosed, it's a shale now, or slate. But anyway, it still preserves the very, very fine compositional banding, which is preserved down to sub-millimeter scale, and that is important because it allows us to make some analysis of the environment in these clays deposits. This is a thin section looked at in the microscope, and you see about a centimeter and a half or something, about a centimeter of rock in the thin section. And again, you can see the very fine preservation of compositional layers in this rock. And the interesting thing you, of course, immediately see is that it has this stripiness between some very light layers and some very dark layers. And, since that is the most conspicuous thing we observe, it's interesting to go closer and see what distinguishes these two types of layers. Here's a little bit closer, one of the light-colored layers. You immediately see that the light-colored layers is slightly more coarse-grained, and you might see, at least if you're a geologist, that it is composed of slightly different minerals from the other layers. These dark gray layers are composed of quartz and muscovite, which is an aluminum silicate, and some dark stuff. I guess they call it dark matter, and that's about it. These light-colored layers, they consist of feldspar, platinum feldspar, biotite, iron titanium oxide, and some quartz. And in composition, these light-colored layers would be equivalent to a volcanic ash layer. And what's interesting is that they contain absolutely none of this dark matter. So we have layers, sub-millimeter size layers that contain none of this dark matter, and some other layers that contain abundant amounts of it. And you can imagine that these layers are chemically equivalent to clay, which deposits very slowly on the ocean floor. We have just a very, very slow drizzle of clay particles plus something dark on the ocean floor. Every now and then you have a volcanic eruption somewhere in the neighborhood. Ash layers fall. They precipitate very rapidly. So they just fall down as an ash layer. It doesn't include any of the dark stuff. But what this tells us is that the dark stuff, which we are now very anxious to find out what is not something that's introduced to the rock at a later stage, but is part of the sediment when it forms. So that is important for this interpretation. Okay, if we look, this is not a cluster of galaxies, but it is a thin section of a rock at high magnification. And again, you see the cause for the dark color in the dark layers is these little round particles that are about 2 to 5 microns across, and they are, if you examine them a little bit closer, it turns out that they are formed of graphite, of carbon, and that is in itself, of course, very exciting because in Earth's surface environment, carbon is usually oxidized either to carbonate or CO2 or bicarbonate in the water or something like that, and usually not formed in its elemental form. Of course, it could form by abiotic chemical processes, but that's very rare. And what you see is in the open ocean that through several meters of this deposition, every day through probably millions of years, we have a steady rain of carbonaceous material onto the ocean floor. And that is very difficult to explain by processes and deposition of organic matter from some sort of organic source. But again, this is of course not a certain thing, so we have to go in and look at the carbon isotopic composition of these particles. And what we see is that there's some spread which we can actually correlate with petrographic observations like interaction with carbonic fluids and whatever CO2, giving you the values down this end, and the best preserved samples petrographically have values up in this end. So they have a deficit, about 25 per mil deficit in 13C compared to the standard we use, which is the carbonate, or about a 20% per mil deficit compared to bulk earth. So they are strongly fractionated in their carbon isotopes. And the way carbon isotopes work, usually in the surface environment anyway, is that most chemical processes do very little to the isotopic ratio, but biologic activity produces biomass that is down in this region, and our biomass from West Greenland is down in this box here, down up here, exactly overlapping with the field of biogenic carbon in anywhere else in Earth's history. So I think that although this is circumstantial evidence, we don't have any morphological indicators of the organisms. One could argue that the carbon in these rocks formed by the steady sedimentation of planktonic organisms that, as they died, would rain to the ocean floor and precipitate together with the clay. And that is a method that, of course, is completely equivalent to what you see on the ocean floor today. So this interpretation would allow us to suggest that life flourished on Earth 3.8 billion years ago, maybe not in this exact form, but some sort of life was there. And this life was very active also. There's about up to a half weight % carbon in the sediment, so it is a very efficient biosphere we have at that time.
So how does that compare to the sedimentation today?
It is actually shockingly similar to what you would find in there's always complications because we have heterotrophic reworking of the carbon and whatnot. So you can have anything from 0 to a whole lot in sediments today. But you can find many phanerozoic sediments that have exactly the same composition in terms of carbon, both isotopic and bulk content. So, and let's try to see if we can find out who these little things were, what were they doing, how did they earn their life. And since we again have no morphological or any other criteria to go by, we try to look at how did they interact with their environment, what sort of metabolic strategies were they applying, were they of such a kind that you can see them today. And as you know, living organisms have two major ways of living. Either they sled downhill on existing potential gradients and they just extract energy, chemical energy from their environment, or they can reverse the build gradients by converting solar energy into chemical energy. And particularly the last one is, of course, one that's going to put a big footprint in the environment because if you just write on existing potential gradients, you sort of just catalyze processes that would otherwise take place. But what we are getting at here is to see were these organisms able to change their environment in any significant way. And clearly, one of the key things that we could look for would be fractionation of redox-sensitive components in the aqueous environment. And you could find a number of redox-active components, but as I've already told you, these rocks have been through metamorphism with all sort of abuse, so therefore any trace element you measure in them might be not very sort of robust towards observation. So we have chosen to look at a couple of elements, namely uranium and thorium, because they have both occurred in the material that are eroded and pouring into the ocean. They occur both in the same minerals, but they have the difference that in oxic environments, the uranium can be oxidized and brought into a soluble form that can be transported as a solute in the water, while thorium cannot be oxidized and does not form any soluble complexes in the Earth's surface environment. And therefore, if you have an oxic, not anoxic, if you have oxic environments, you can separate uranium from thorium. If you have anoxic environments, they will be transported together. And uranium and thorium have the beauty that they leave an isotopic track in the lead isotopes of when they were first introduced into some system. And particularly uranium is beautiful because it has two radioactive isotopes, one of which is almost extinct today. And if you have the lead isotopes from the 235 uranium, if you have a high abundance of the daughter product, the 207 lead, then you know that this uranium must have been introduced to your system very early in your system, so there's no chance of changing it at any later point in time. So we have been looking at uranium and lead, not directly uranium and thorium, but we've been looking at lead isotopes in these rocks. And what you see is, this is the average Earth growth curve. This is this little pathetic green thing here. And these are usually most rocks we analyze will fall somewhere under this curve, somewhere in this general area. But what you see for these sediments is that they are extremely radiogenic in lead isotopes. That is in itself interesting because that shows you that the sediments were rich in uranium. This is exactly what you see today in organic rich sediments because you transport the oxidized uranium form into this basin, but when the organisms decay and die and produce local reducing environments that scavenge uranium out of the water and concentrate it in the sediment. So what we see here is that the oldest sediment existing on Earth also concentrated uranium from seawater, exactly the same way as you see today. We can also see from the array of data that the rocks were subjected to metamorphism 2.8 billion years ago, and that creates some complication. This is a line for the sediment, and this is a line for other rocks in that general area. You can see that these organic-rich sediments are displaced from the ordinary ones in this 2.8 billion year event. That means that they started out somewhere with a very radiogenic composition already 2.8 billion years ago. We can model this, and we can tell that the sediments have about 5 times higher uranium content than average across the means that they were extremely enriched in uranium at that time. So one part of our study shows, okay, uranium was probably transported in a solute manner and incorporated into this sediment. It could be, of course, that it also had a high thorium at that time. We need to test that. So let's go on to the thorium lead, which is this axis, and this is the 238 uraniogenic lead over here. What we see is the thorium data form an array. This is again the Earth, the crustal curve we have here. What we see is that it's displaced to this side, and the starting composition 2.8 billion years ago, when the last disturbance of the system was down here. What this indicates is that the rocks during early Earth history evolved with extremely low thorium compositions and extremely high uranium compositions. This leads us to a model suggesting that we had an oxidized veneer in the ocean at that time, and we had a reduced bottom water property where we could deposit all this stuff. Anyway, the main conclusion from this is that at that time we were not here at the stem of the tree of life. There will be way up in the ground region. Oxygen photosynthesis, which is what we think we have identified, is an invention by cyanobacteria or something in that order. So that would suggest that we are up here and that life must have started considerably earlier on Earth compared to that. Okay, now we should go to the really speculative part of this, if this is not bad enough. This is just getting you 5 minutes of the possible consequences of this first. On a lifeless planet, solar energy is just beaming down the surface, converted to heat, and radiated back out again. And you can see from Earth's energy balance here that we have about 340 watts per square meter of solar energy just completely lost from the system, just not put to use. All the geologic processes have to deal with these pathetic 87 milliwatts per square meter coming from crystallization of the core and radioactive decay in the Earth. So Earth could really use some of these 340 milliwatts, watts. And the reason why these watts don't do much is, of course, that the individual photons have not strong enough energy to break, for instance, the hydrogen-oxygen bond in water and do chemical work. So therefore, again, they're just converted to heat and back radiated. Until you develop the ability to form a chlorophyll molecule, which has the beautiful capability of storing energy from several consecutive photons until we have enough to do something constructive with it. This constructive thing being split in water into hydrogen and oxygen, combining with hydrogen with CO2 and form sugar and oxygen, which is a basic photosynthetic reaction. So chlorophyll, which we think was invented 3.8 billion years ago, is a molecule that suddenly puts the solar energy into chemical use on planet Earth. You don't lose it as heat into space again, but you can actually use it for something. And how much energy goes in this reaction? Well, you can go and find your thermodynamic data tabled down in Ocean. And what you see is that you have per 100 grams of this reaction, you convert 1,700 kilojoules. Let us try to see if this is an abundant process on Earth. Well, it seems so. This is a picture of Danish, the North Sea. On a winter day, you can see cyanobacteria all over the place. Our planet is completely covered in bed of chlorophyll molecules, harvesting photons, and transforming them into chemical energy. So if you just take the annual photosynthetic conversion of solar energy into chemical energy, it turns out that you use 10 to the 16th mole of carbon per year, which is equivalent to 300 milliwatts per square meter of Earth every day, every 24 hours a day, you actually you convert 300 milliwatts of solar energy into chemical-free energy on the surface of Earth. You compare that to what we thought was geologists' driving force, the 87 milliwatts down here. They don't work for anything. This is the real thing. So you could speculate the geological processes really start to speed up and really do something by the time you could tap into this source. And that is my postulate here, is that this tapping into that was actually what is driving the weathering cycle, a little bit comparable to what Uffe said. Our atmosphere is out of equilibrium with the surroundings. Without life, these two things would equilibrate and nothing more would happen. Weathering would stop. We wouldn't have any particular interesting things happening. But since life is keeping atmosphere out of equilibrium with the substrate, the atmosphere keeps the weathering cycle going, and we break down the materials. And the weathering cycle is a key and essential part in the chain of processes that lead to the formation of granite. So when you look at a mountain like this, this postulates that it is relatives of these two things that actually build this thing. That the granites, the continents that we have on Earth, that they are actually formed as a consequence of the presence of life on our planet. And we can try to test this by some statistical means. We can say, okay, how many planets do we know that have life? 1. How many planets do we know that have granite? 1. We actually don't know granite on any other planet, so our statistical test shows us that it's not that life forms the granites. You can also take another one, this is more historical approach, and say, okay, how old is Earth? It's about 4.5 billion years if you really get it self-consolidated. And so, how old are the continents, the granites on Earth? They're about 3.8 billion years old. And no, nothing is older. And from isotopes and other systems, we can tell that there's no older continental components in any ancient sediments. So everything suggests that Earth waited about 700 million years before it started to form continents. And why did Earth wait 700 million years before it got its act together and started to form continents? Well, students would argue maybe the continents were destroyed by meteorite bombardment or something. We know that meteorites didn't resurface any other planets that we know, the moon or anything. We just maybe it was dense in the surface, but they didn't destroy ancient surfaces. So we have to look for some internal explanation on Earth why granites only started to form 2.8 billion years ago. And of course, the answer comes from the sediments. Oxygenic photosynthesis was active 2.8 billion years ago. You got enough energy to start making some continents. Before that, you could forget about it because there's not energy enough in the system to build the continents. So I think with this proof of my hypothesis, I will proceed to the end.
Thank you very much, Minik. Any questions for me?
So I've heard before that you won't find mountains and I guess continents. You don't have water because for you to have to have the crust to glide appropriately and so forth. But you extend that to be that you need life to. Well, what is the argument?
The argument is that life puts 300 milliwatts per square meter of chemical energy into the weathering cycle, and the weathering cycle is a key component in granite formation. But if you take the rocky material on the planet and start heating in the form of basalt, the basalt goes up on it due to buoyancy, it just goes up on the surface, cools. And if it's a planet that has some water in the mantle, so the mantle has a low enough viscosity that you can subduct things again, you take the basalt back down again, you mix it back into the mantle, and you can melt again, make another basalt again. But what you need is something to differentiate the basalt material in a way that you can extract some other metals from the basalt. And that's what when you weather the basalt and make a sedimentary pile that contains, you sort of differentiate the basalt into various constituents, and then you put those down to melt them, you start to form granites in a large way. You can form granite, technically you can form granite in very small amounts from just basalt, but it forms so small amounts in just the basalt you cannot separate it. mechanically.
No, but I think I'll buy that, but I don't understand why can't you make continents? Why? Well, it's your vision of the...
Because a continent is something that is buoyantly stable, which consists of granite, basically.
Okay,
Basalts are not buoyantly stable. When basalts thick enough pile, they actually becomes denser than the mantle below due to the pressure conversion of the so that's what it is. The system is a granite.
I like your story.
So do I.
Yeah.
Core before this research
Now you talked about the detection of life from being out of. You wouldn't have eating animals or life energy. You wouldn't be that right.
No, I think what we need is the life that is just already existing reaction. Maybe they do some fractionation while doing so that you could identify somewhere. Very possible. But the large interplanetary scale requires that you can convert something that is not chemical energy into chemical energy, which you can identify. I think that is, and the Tokyo system is exactly one that requires that you have a flow of energy to tap into energy.
But you have, I mean, for instance, the system species which are not.
Ozone is life created in the sense that the oxygen is life created.
Well, okay, yeah.
Yes, Brian and
Just an economic statistical saying, then any previous active hydrosphere on Mars would then ended when life got extinct there? Or?
Well, you mean it failed to have Mars was partly caused by the inaptitude of the bio?
Yeah.
I don't know. I think that the shape of within what this is very likely something that is you can unlike for. But I don't know.
Continents on Venus, would you consider this as another proof of your theory?
Absolutely, it's a final proof. No, I think that Venus is a completely different thing, of course, because Venus does not have plate tectonics the same way as we have it. It probably has some sort of just superheats in it. I think that I don't know whether you necessarily would preserve even buoyantly stable things in such a chaotic situation like this. On Earth, it's a very orderly and slow proceeding process that actually means that when first formed continental material, you cannot get rid of it again, just because there's no way of getting it. It's subducted.
Steen?
So these very ancient basalts. So I mean, one of the things that seems to be clear from analysis of existing life forms is that you have, and you showed that tree, that photosynthesis is something that happened quite late in the evolution. So you must have been eating. You must have these first bugs. They must have been eating. They must have been living off the rocks.
Absolutely, yeah.
For gasity.
Yeah. So
what you're saying, but what you're saying is that it has to be that since we couldn't have had any continent, we couldn't even have had islands.
I don't.
But that means that you everything would have been.
You have islands. You have Iceland is not a continent. The Azores are not a continent.
Okay, so you could still because
you can emergent land, but that doesn't make a continent.
Yeah, but then what you're saying is that land masses, they would have been shortly lived.
Yeah, land masses would be processed and go down again. You can see like the Hawaiian chain. You just see that actually they're sinking by their own density and disappearing. I mean, some part of it is just that they're raining away and so forth, but actually most of the lack of the whole chain is that they're actually sinking by their own gravity. So, which doesn't happen to a continent. They just sit there.
Okay, but this now I start to worry a little bit because if you that means that you would have. I mean, how do you know what the salt concentration of the waters were? Because if everything was under salt water, then how
it wouldn't make any difference to salinity.
No, it will make a big difference to what you can do chemically.
Yeah, no, I agree. But on a geologic timescale, when first you attain equilibrium, I mean, it doesn't matter. You won't have any significant amount of the rocky material in solution, even in high saline ocean. And by the time you reach saturation, you won't work. It won't perform work anymore. Your water. if that's what you're getting at.
No, I'm getting at, well, what would it be in the pore space if you are under several kilometers of water? So what would you have? Would you still have water with low salinity?
I don't know. If you go into the present crust, if you just go below you actually have highly saline brines moving around anyway. Even today, you have 48% salt in many hydrothermal fluids.
I hate to interrupt you too, but I think we move on to the next speaker, and then there's only the coffee break on 20 minutes, so maybe you can stay till the coffee break. Then I'd like to introduce Kai Finster from Aarhus University, and in Aarhus they have actually built a small little piece of Mars on which they conduct experiments, and will give us some maybe interesting answers about if there's life on Mars now that people too fail.
No, I don't think I will give you some answers, but I would like to introduce you to some approaches that we have chosen to study some of the questions which may be interesting. Yeah, myself, I'm an environmental microbiologist and used to work with all different kinds of microbes on Earth. And I'm used to go out into nature and take the samples, and then I can work with this and isolate organisms and study their physiology. This is quite difficult when you want to do studies on Mars. Until maybe 20 or 25 years, it's not possible to get material from there or to do experiments on Mars. So we have to deal with what we have on Earth. And of course, we're making one big assumption, and then this assumption is that life on Mars is DNA-based life, which looks like the life that we know from Earth, and that it behaves the same way. And when we accept this assumption, then we can do some studies and ask what would happen if this planet Earth turned into a scenario and went to become Mars. Would life be able to persist under these conditions? And this would be very important when we want to search for life on Mars. As it looks now, it is very almost sure that life is not present in the surface of Mars due to several physical and chemical conditions which are not very favorable to life. But maybe life could persist in deeper strata in Mars. It would, of course, require digging or at least different kinds of research than the ones that can be done by the rulers which are out there. But I will show you what we just started with this 2 years ago. So we're in a very early phase of our research, and we came into this by chance. Just the people from the geological department, the physics department asked if we were interested in studying some iron minerals in Jutland, which were particular, and we said yes, we could be interested in this, and then from this collaboration, a group started, and we started to develop some equipment which we think could be very useful in these kinds of investigations.